So for tangent lines of piecewise functions, this is kind of a special case where your function is defined as a piecewise function and you're trying to decide whether you can write a tangent line. So there are two things you want to check if you're checking to see if you can write a tangent line of a piecewise function. The first thing you want to check is for continuity. For continuity, you're checking the function itself. You're checking to see if the function itself has the same limit as x approaches c from both directions. We had a whole packet on that in my class, but you're just checking to see if those two limits match. Usually those two limits are just straight substitution limits, not always, but usually, and so you just have to substitute your breaking point, the point you're checking, into both halves of your piecewise definition. And then the next thing you want to check is you want to check to see if both halves have the same slope. You might have to use calculus to find the slope, but you might not. You might have a linear piece of your piecewise function. You don't have to use calculus on a linear piece. All right, we're going to do some examples of these. So for this example, does this function have a tangent line at x equals 3? If so, what is its slope? So the first thing you want to check is you want to check for continuity. And the way you check for continuity is you take the limit as x approaches 3 from the positive direction, which would be the top half of the definition. So that would be 6 times 3, which is 18. And then you take the limit as x approaches 3 from the negative direction. And then you'd use the other half of the definition, which would give you 9. And since they don't match, it's not continuous. So no, you don't have a tangent line because you don't even have a continuous function. If you take a look at a picture of what we're dealing with a jump discontinuity. It doesn't have to be a jump. It could be also a hole. But if there's any type of discontinuity at all, then you can't write an equation for a tangent line. Your function does not have a tangent line at a discontinuity. So stop. Don't do any more calculus. You already know that you can't do it. Okay, so we did a minor adjustment, and I trust that this adjustment would make this function continuous, but let's prove that to ourselves. So the limit as x approaches 3 from the positive direction is still going to be 18. And the limit as x approaches 3 from the negative direction is going to be 2 times 9, which is 18. So yes, we now have continuity, and so that's the first step. Now we're going to check to see if the slopes match. So as x approaches 3 from the positive direction, I'm going to encourage you not to use any calculus. The line 6x has a slope of 6 because that's a straight line. As x approaches 3 from the negative direction, we're going to use the other piece of the definition, and that is a curvy line, so we have to use some calculus. So we have f of 3, which would be 18, and we have f of 3 plus h, and that would be 2 times 3 plus h squared, which would be 2 times 9 plus 6h plus h squared, which would be 18 plus 12h plus 2h squared. So then we're going to set up our difference quotient for the problem. So we have the limit as h approaches 0 from the negative direction, actually, because we're going at 3 from the negative direction, although this part doesn't really matter. So then we're going to take 18 plus 12h plus 2h squared minus 18. There's our difference quotient divided by h. Notice that the 18 subtract away, so we have the limit as h goes to 0 from the negative direction of 12h plus 2h squared over h. We can now plug in a 0 and notice that we have 0 over 0, which means we should be able to factor something away to help ourselves. And it looks like we can factor an h out of the numerator, so we have 12 plus 2h over h. Now our h's can cancel, and as we approach 0, the slope would be 12. We said that the slope here was 6, the slope here is 12, so we cannot write an equation for the tangent line there. So then our last example, so I just wanted to visually show you what that means. So the 6x is a straight line, it's approaching this parabola, and I couldn't write a tangent line because I can't figure out what the slope is at that curve. It has a slope of this, but it also has a slope of this. So since they have two different slopes, I can't write an equation for a tangent line at x equals 3. I'm going to leave it as an exercise to you that this example does fix the problem. This tangent line does exist at x equals 3, and the visual for that is that line 6x meets up with the parabola x squared plus 9 in such a nice way that now the two slopes match, the function is continuous, and so I could write an equation for a tangent line at x equals 3, and the slope would be 6, and the point would be 3, 18, and it would all be possible to write that tangent line equation. So I want to give you a warning. Some of you already know how to find derivatives using shortcuts. Some of you are in physics. Some of your pre-calculus teachers may have taught you some shortcuts. And using the shortcuts is definitely important, and you will be assessed on those shortcuts later in the year, but you will not be assessed, on using shortcuts on the Chapter 2 test. So you must use limits to find slopes on the Chapter 2 test. Take a minute, summarize what you know about tangent lines. Remember that we just did some baby calculus, so there's another picture of my baby. See you in class.